When altering a three-phase electrical service, maintaining the correct phase rotation is crucial for the proper operation of connected equipment. Incorrect phase rotation can cause motors to run in reverse, potentially damaging machinery and creating safety hazards. Understanding which leads can be changed and which must remain in their original configuration is essential. The leads that can be changed are any two of the line leads typically labeled A, B, or C. Swapping any two of these leads will alter the phase rotation. This can be done intentionally to correct an incorrect rotation or unintentionally if care is not taken during the reconnection process. It is important to note that only two line leads should be swapped at a time. Swapping all three line leads will not change the phase rotation. Furthermore, the leads that cannot be changed are the neutral lead, typically labeled N, and the ground lead, typically labeled G. These leads serve critical safety functions and must remain connected in their original configuration. The neutral lead provides a return path for imbalanced currents in the system, and the ground lead provides a path for fault currents to flow back to the source, tripping circuit breakers or fuses and preventing electrical shock hazards. Altering the neutral or ground connections can create dangerous conditions and should never be done. To ensure correct phase rotation after a three-phase service change, it is recommended to first identify and label the existing leads before disconnecting them. This can be done using color tape or wire markers. Then, after the service change, reconnect the leads in the same configuration as before. Finally, verify the phase rotation using a phase rotation meter before energizing any connected equipment. If the phase rotation is incorrect, swap any two of the line leads to correct it. In summary, when changing a three-phase service, you can change any two of the line leads, A, B, or C, to adjust the phase rotation. However, the neutral lead N and the ground lead G must never be changed. Doing so can create dangerous conditions and damage equipment. Always verify the phase rotation after a service change to ensure the proper operation of connected equipment. Three-phase power systems are fundamental to many industrial and commercial applications, and a solid understanding of phase rotation and lead identification is crucial for anyone working with these systems. Firstly, understanding the importance of phase rotation is crucial. Phase rotation refers to the sequence in which the three phases of a three-phase power system reach their peak voltage. This sequence is typically either a BC or a CB. Secondly, the direction of rotation is critical for the proper operation of three-phase motors and other equipment. If the phase rotation is incorrect, a motor will run in reverse, which can damage the motor itself or the equipment it is driving. Thirdly, identifying the leads correctly is also essential. In a three-phase system, there are three line leads typically labeled A, B, and C, and a neutral lead N and a ground lead G. The line leads carry the three phases of the power. The neutral lead provides a return path for imbalanced currents, and the ground lead provides a path for fault currents to flow back to the source. Fourthly, the neutral and ground leads are safety features. The neutral lead allows for the use of single-phase loads on a three-phase system, while the ground lead protects against electrical shock hazards. Fifthly, it is important to note that the color coding of the leads can vary depending on the region and the specific electrical code. However, generally, black, red, and blue are used for the line leads, white or gray is used for the neutral lead, and green or bare copper is used for the ground lead. Sixthly, when working with three-phase systems, it is always recommended to use a phase rotation meter to verify the phase rotation before energizing any equipment. This meter will indicate the direction of rotation, allowing you to correct it if necessary. Seventhly, remember that swapping any two of the line leads will change the phase rotation. This is the only way to correct an incorrect phase rotation. Eighthly, never attempt to change the neutral or ground leads. These leads are critical for safety and should only be connected in their original configuration. Ninthly, if you are unsure about any aspect of working with three-phase systems, it is always best to consult with a qualified electrician. Working with electricity can be dangerous, and it is important to take all necessary precautions. Tenthly, always follow the applicable electrical codes and safety regulations when working with three-phase systems. These codes and regulations are designed to protect you and others from electrical hazards. Let's delve into more detail about the implications of changing the phase rotation and the specific safety concerns related to the neutral and ground leads. When we talk about changing phase rotation, we are essentially altering the order in which the voltage peaks occur on the three phases, A, B, and C. Imagine each phase as a wave, and the phase rotation is the sequence in which these waves reach their highest point. If the equipment connected to the three-phase system is designed to operate with a specific phase rotation, say a BC, and you inadvertently connect it with the wrong rotation, a CB, the effects can range from inconvenient to catastrophic. As mentioned earlier, motors will run in reverse. This might seem like a minor issue, but in many industrial applications, the direction of rotation is critical for the functionality of the driven equipment. For example, pumps designed to move fluids in one direction will simply not work if the motor is running backwards. Conveyor belts will move in the wrong direction, potentially causing materials to fall off or create jams. More seriously, some equipment, like certain types of compressors or specialized machinery, can be severely damaged if they are forced to run in reverse. Internal components might be stressed beyond their design limits, leading to premature failure or even a complete breakdown of the machine. Now let's consider the neutral and ground leads. These are not simply wires that complete a circuit, they are essential safety components that protect both equipment and personnel. The neutral lead in a three-phase Y-connected system provides a return path for unbalanced currents. In a perfectly balanced three-phase system, the currents in all three phases are equal, and the neutral current is zero. However, in the real world, loads are rarely perfectly balanced. This means that some phases will carry more current than others, and the neutral lead provides a path for this difference in current to flow back to the source. If the neutral lead is disconnected or improperly connected, this imbalanced current has no return path. This can cause the voltage on the phases to become unbalanced, leading to overheating of equipment, voltage fluctuations, and potential damage to sensitive electronics. In extreme cases, the voltage imbalance can become so severe that it can cause insulation breakdown and equipment failure. The ground lead, on the other hand, is a dedicated safety conductor that provides a low impedance path for fault currents to flow back to the source. A fault current is an unintended flow of electricity from a live conductor to ground, typically caused by a short circuit or insulation failure. If a piece of equipment has a faulty connection, and a live wire comes into contact with the metal chassis, the ground lead provides a path for the fault current to flow back to the source. This high current flow will trip the circuit breaker or fuse, disconnecting the power and preventing a potentially lethal electric shock. Without a properly connected ground lead, the fault current might not be sufficient to trip the breaker. This means that the metal chassis of the equipment could become energized, posing a serious electrocution hazard to anyone who touches it. Furthermore, the absence of a proper ground connection can also increase the risk of fire. If a fault current is not quickly interrupted, it can generate heat, which can ignite nearby flammable materials. Therefore, it is absolutely critical to ensure that the neutral and ground leads are always properly connected and never altered. These leads are not just wires, they are essential safety components that protect both equipment and personnel from electrical hazards. Always consult with a qualified electrician if you have any doubts about the proper connection of these leads. They have the knowledge and experience to ensure that your electrical system is safe and reliable. Now let's explore some practical scenarios and best practices for working with three-phase systems to reinforce these concepts. Imagine you are tasked with replacing an existing three-phase motor in a factory. The old motor has failed and you need to install a new one. Firstly, before you even begin disconnecting the old motor, carefully label all the leads. Use color tape or wire markers to clearly identify the A, B, and C phases, as well as the neutral and ground leads if they are present. Take a photograph of the wiring configuration for reference. Secondly, disconnect the old motor, making sure to de-energize the circuit beforehand to prevent electrical shock. Thirdly, install the new motor, carefully connecting the leads according to your labels and the photograph you took. Fourthly, before energizing the new motor, use a phase rotation meter to verify the phase rotation. Connect the meter to the A, B, and C phases and observe the indicated rotation. If the rotation is correct, you can proceed to energize the motor. Fifthly, if the rotation is incorrect, swap any two of the line leads such as A and B, and recheck the phase rotation. Once the rotation is correct, you can energize the motor and verify that it is running in the correct direction. Sixthly, if the motor is still running in the wrong direction after swapping two leads, double-check your wiring and the phase rotation meter. There may be an issue with the motor itself or with the meter. Seventhly, if you are working with a three-phase panel board, it is important to ensure that the neutral and ground buses are properly connected and grounded. The neutral bus should be connected to the grounding electrode conductor, which runs to the grounding electrode system, such as a ground rod or a metal water pipe. Eighthly, the ground bus should be bonded to the metal enclosure of the panel board. Ninthly, never use the neutral conductor as a ground conductor, or vice versa. This can create a dangerous situation where the metal enclosure of the equipment becomes energized. Tenthly, always follow the applicable electrical codes and safety regulations when working with three-phase systems. These codes and regulations are designed to protect you and others from electrical hazards. Let's delve deeper into the specific code requirements related to three-phase systems. The National Electrical Code, or NEC, contains detailed requirements for the installation and wiring of electrical systems, including three-phase systems. NEC Article 200 addresses the identification of grounded conductors, which is typically the neutral conductor in a three-phase system. It requires that the grounded conductor be identified by a continuous white or grey outer finish. NEC Article 250 covers the grounding and bonding requirements for electrical systems. It specifies the size and type of grounding conductors, as well as the methods for connecting grounding electrodes. NEC Table 250.122 provides the minimum size of equipment grounding conductors for various sizes of overcurrent protective devices. NEC Article 310 addresses the requirements for conductors for general wiring. It specifies the ampacity of conductors, as well as the requirements for insulation and protection. NEC Table 310.16 provides the allowable ampacities of insulated conductors rated up to 600 volts based on the insulation type and ambient temperature. NEC Article 430 covers the requirements for motors and motor circuits. It specifies the requirements for motor overcurrent protection, motor disconnecting means, and motor branch circuit conductors. NEC Table 430.250 provides the full load currents for three-phase alternating current motors. NEC Article 450 covers the requirements for transformers. It specifies the requirements for transformer overcurrent protection, transformer grounding, and transformer ventilation. NEC Article 700 covers the requirements for emergency systems. It specifies the requirements for emergency power sources, emergency lighting, and emergency circuits. NEC Article 701 covers the requirements for legally required standby systems. It specifies the requirements for standby power sources, standby lighting, and standby circuits. NEC Article 702 covers the requirements for optional standby systems. It specifies the requirements for standby power sources, standby lighting, and standby circuits. It is important to note that the NEC is a minimum standard, and local jurisdictions may have additional requirements. Always consult with the local electrical inspector to ensure that your electrical installation complies with all applicable codes and regulations. Furthermore, it is crucial to stay up to date with the latest edition of the NEC, as the code is revised every 3 years. Changes to the code can affect the design and installation of electrical systems, so it is important to be aware of these changes. Now, let's discuss some common troubleshooting techniques for three-phase systems. If you are experiencing problems with a three-phase system, such as a motor running in reverse or equipment not operating properly, there are several steps you can take to troubleshoot the issue. Firstly, verify the phase rotation using a phase rotation meter. If the phase rotation is incorrect, swap any two of the line leads to correct it. Secondly, check the voltage on each of the three phases. The voltage should be balanced and within the acceptable voltage range for the equipment. Thirdly, check the current on each of the 3 phases. The current should be balanced and within the allowable current range for the equipment. Fourthly, check the connections to the equipment. Ensure that all connections are tight and secure, and that there are no loose or corroded wires. Fifthly, check the overcurrent protective devices, such as circuit breakers or fuses. Ensure that they are properly sized and that they are not tripped. Sixthly, check the grounding system. Ensure that the grounding conductors are properly connected and that there are no open circuits or high resistance connections. Seventhly, if you suspect a problem with a specific piece of equipment, disconnect it from the system and test it separately. This will help you isolate the problem. Eighthly, if you are unable to troubleshoot the problem yourself, consult with a qualified electrician. They have the knowledge and experience to diagnose and repair complex electrical problems. Ninthly, always follow safe electrical practices when troubleshooting electrical systems. To energize the circuit before working on it, and use appropriate personal protective equipment such as insulated gloves and safety glasses. Tenthly, document all of your troubleshooting steps and findings. This will help you track down the problem and prevent it from recurring in the future. In addition to these troubleshooting techniques, it is also important to perform regular maintenance on 3-phase systems. This includes inspecting the wiring, connections, and equipment for signs of wear and tear, and cleaning or replacing components as needed. Regular maintenance can help prevent problems from developing and extend the life of the equipment. In conclusion, working with 3-phase systems requires a thorough understanding of phase rotation, lead identification, and safety procedures. By following the guidelines and best practices outlined in this discussion, you can ensure that your 3-phase system is safe, reliable, and operates properly.